accepted our invitation for giving a talk in the John Conway Patriot Seminar Series. So Professor Welker is currently affiliated with Marburg University. He's very well known for his work in subdivision of simplicial complexes and many theories related to it. And one of the associated topic is spaces of real polynomial with restricted root, what he will be talking about. And particularly, these are few recent developments. So welcome everyone in the John Conway Patriot Seminar Series. Over to you, Professor Welker.
Okay, thank you very much for the invitation to talk in your seminar. So my talk today will be about a very classic subject, about polynomials. And in some sense, the point of view I'm taking is an undergraduate viewpoint. I will be looking at root multiplicities. So this is all I'm saying today is joint work with Boris Shapiro from Stockholm University and Gabriel Katz from Boston. Okay, so what are we looking at? So our actual work considers two types of objects. So one of them are the polynomials. So we consider polynomials of a fixed degree, and we have real coefficients, and the polynomials are monic, so the coefficient of the top degree power of x is 1. Okay, so we collect all of those and we give them a topology, namely by using the topology from real D space, where we get the coordinates or the point in real D space from our polynomial by just looking at the coefficients. Okay, so we collect the coefficients in a fixed order, in a ascending degrees order, and then we get some point in R to the D. For a polynomial of degree D, we have D plus 1 coefficients. The top degree, as I said, is coefficient is set to 1, so we ignore that one, and we can identify the space of real polynomials of fixed degree D with R to the D. So this is what I will focus on in this talk. There is a second space, a related space, where our methods extend to. Actually, we have to prove, for proving something about this space, we sometimes have to prove something about this slightly more complicated space. Namely, this is real binary forms. So instead of a polynomial in a single variable, now we have two variables, x and y. And we consider forms of a fixed degree D. And so we have y to the d minus 1x, up to y to the x to the d minus 1, up to x to the d as the monomials that appear in such a polynomial. Then we have coefficients. And we allow all coefficients except for the all zero coefficient. Okay, so in particular, this binary form will be of degree D because it will be non-zero, and it has only monomials of degree D in its expansion. But now, instead, in contrast to what we do here, we do not give it a topology. It inherits from these coefficients. Rather, we take the space modulo projective equivalence. So we consider two binary forms equivalent if they are the same after multiplication with a real constant. And this way we can identify this space of binary forms with real projective D space. But as I said, we won't consider, in this talk, I do not consider that space, but I would like to mention that one can decompose this space of binary forms into spaces of polynomials of degrees 0 to D. And this you achieve the following way. You take one of those polynomials, say p to the d, from p to the d, pd or pi, And you map this polynomial to y to the d times the polynomial f evaluated at x over y. And what you get is a binary form, and this gives you a disjoint decomposition. That's an easy exercise to prove. So this somehow highlights the intimate relationship between the binary forms and the spaces of polynomials. But as I said before, for this talk, I confine myself to these spaces of polynomials. Okay, object clear, I guess. Any questions? Okay. So our goal is to study subspaces of the space of all polynomials, or in the part I won't speak about binary forms, which are defined by restrictions on the roots.
Hello, Professor.
On the real roots. So I don't bother about which complex roots exist. They can be there or not, but I want to have restrictions on the real roots in the case of the polynomial space. And then in the case of the binary forms, the roots, we have a similar root restrictions, real roots, but we also restrict somehow the multiplicity of the infinity root. And the motivation why these spaces are interesting comes from theorems actually motivated by singularity theory from the school of Arnold. And Arnold himself, for example, proved the following theorem, which was then much later generalized by his student Vasiliev. Namely, they looked at the spaces of polynomials, monic polynomials of degree d, so that this polynomial has no real root of multiplicity greater or equal to k. So for k equals 2, the classical Arnold case, it's the polynomials that have no double real root, kind of a lot of double complex roots, but we really confine ourselves to the restrictions on real roots. And so this space is a subspace of the polynomial space of polynomials of degree d. Just see, I have the subscript wrong here. It's PD usually down. Okay, so monic polynomials of degree d. And this has some topology, and therefore you can look at the cohomology, can look at fundamental groups, and everything essentially is classified in this work by Arnold and Vasiliev, up to the complete description of the product and cohomology. Vasiliev also did something on binary forms, similar work, similar root restrictions, but he did not consider the projectivization that we will need for our work. So this just also exhibits that this extension to binary forms has appeared in the literature in a slightly different form, and it's kind of natural. But the results that were known before are not related to our results. Okay, so now we will describe a generalization of those results for the case of monic polynomials of degree d. And as I said, the case of binary forms can be treated similarly, but it's technically more involved, and therefore I don't want to present the results here in this talk. So we reduce essentially everything to combinatorial data. I mean, we also need to specify what type of generalizations we want to study, and they will be manifested in certain combinatorial data. So we go from a polynomial of degree d, monic polynomial of degree d with real coefficients, and we consider its real roots. There may be none, but okay, I don't care. But we collect them. So they are real numbers, so we can order them in ascending order. And we do that. So we have like the smallest real root, we call that x1. And then this appears with a certain multiplicity, I1. Then there come the I1 plus first real root. And that's actually bigger than the first I1 roots. And then they're equal up to I2. And then we have I2 minus I1 is the multiplicity of the second largest real root. And so you go on up to L. So you say you have L different real roots. And the multiplicity of the Lth one we collect in omega L. So omega 1, omega 2, up to omega L collects the multiplicities of our real roots. So this omega 1 up to omega L is then a L tuple of numbers, of natural numbers larger than 0. And the sum of these numbers must, of course, be less than the degree, or less or equal to the degree. But it must also be congruent to the degree modulo 2, because these are the real roots, and then all the complex roots, they come in pairs. So there must be an even number of complex roots counted with multiplicity. And that's we call the real root pattern of this polynomial, of this fixed polynomial. Now we want to reverse the approach. Instead of starting with a polynomial and considering a real root pattern, we now want to collect polynomials that exhibit the same real root pattern. For that, we first collect all our root patterns in a set omega d. So omega d is exactly all the L tuples for arbitrary L greater or equal to 0. Of positive natural numbers with the property that they sum up to something less or equal to d, and their sum is congruent to d modulo 2. These are the possible root patterns of a monic polynomial of degree d. And when L is 0, that's kind of a degenerate case. We consider this the empty root pattern, sometimes just denoted by the brackets, and we then say that the sum of the root multiplicities in this case is 0. Just as a definition of what is happening in the case of an empty root pattern for L equals 0. And then we also need for later study, we need the following kind of the norm of such a root pattern. Omega 1 up to omega L is this just the sum, essentially saying it's the number of real roots counted with multiplicities. Okay, now these are combinatorial objects, and to each of these combinatorial objects, we now associate a subspace of the space of polynomials, of monic polynomials of degree d. Now, this subspace consists of all polynomials that have exactly this root pattern. Okay, so we fix a root pattern, and then we collect in the number d, and then we collect all polynomials that have this exact root pattern. And this is not an arbitrary space. It's a very nice topological ball. It's a cell that can be easily seen. Namely, if you have such a root pattern, omega 1 up to omega L in omega d, then how is this space described? Now, the space is described either by the coefficients, or homeomorphically, you can also look at the roots, because polynomial is completely defined by its coefficient and by its roots. So here we have roots, L different real roots. And the way we describe this root pattern, we have the omega 1 belongs to the smallest root and omega L belongs to the largest root, real root. And there is a less or equal inequality between the roots. So if I have like x1 belongs to omega 1 and xl belongs to omega L, that's the corresponding root, then these roots must satisfy x1 less than equal up to xl. And that defines a simplicial cone. So the real numbers satisfying these inequalities in RD satisfy a simplicial cone of dimension L. So that's kind of the first ingredient to define a polynomial here. Now, the second ingredient is, okay, you have complex numbers. They are the roots, the complex roots that you don't see. And now, of course, a complex root of a truly complex root of a real polynomial comes with a sibling, with its conjugate root. So therefore, we can describe the set of complex roots as you take for each complex root, you take a half plane in R2, the upper half plane. Say you say the imaginary part is positive, and this automatically a point there determines another root. And then, of course, you can take a product of that's this here. This number describes how many complex roots. So D minus the number of real roots describes how many complex roots there are. Since they come in pairs, you only need to describe half of them. And then you take for describing them, you take points in these half planes. You take the direct product of these half planes. And then since they are roots, you don't know in which order they come. So you need the symmetric product. So you take the direct product of that many half planes and you mod out by the action of the symmetric group. And then classic topology tells you that this is again a ball. Okay, so altogether you get a description of this object as a ball. It's a L plus D minus this norm of omega cell. Okay, so this allows you now to define a very nice cellular stratification of your space. And I have a very simple calculus high school example for that. So look at the polynomial of degree 2. So D is now 2. We have 2 coefficients. We write this coordinate axis we label with the coefficient a1, with the coefficient of x. In this coordinate axis we label with a0. Now we know when does this polynomial have a double root. It has a double root if a1 squared equals minus 4a0. Okay. So this means a0 is 1/4 over 1a times a1 squared. So that's exactly this orange parabola. But double root in our notation with these root multiplicities correspond to this root multiplicity. I have to maybe write a bit larger, 2. I have a single root with multiplicity 2. Okay, and then wait a second, that's wrong. Actually, I had a 0 plug in, and then if you are above, then a0 is larger than 1/4 a1 squared, and then we have no real root that corresponds to the empty root pattern. This one here, maybe also label that one. This one corresponds to the empty root pattern. So the whole space here, this above the parabola, the open cell here, is a cell of dimension 2, and this corresponds to this root multiplicity. And below we have 2 different real roots corresponding to root multiplicity 1, 1. And again, you easily check that the space below this parabola is a 2 cell. Okay, is this picture clear? Is there any questions about the picture and our definitions?
No question. I think
okay.
Everything is clear. Thank you.
Okay. So now this means also that essentially we can decompose the whole space of polynomials of degree D into cells according to root multiplicities. And so we get a cellular decomposition of this space. And then you can, of course, ask, how are the cells, what is the neighboring of these cells? Which cells borders another cell? And this is again described in combinatorial terms. Namely, you take a root multiplicity and you want to know which, so to this root multiplicity belongs a cell. It's an open cell. And you want to know which polynomials lie in the boundary of this open cell. And there are two operations that can lead to boundary polynomials. The first one is you take these entries here of this root multiplicity and you add two consecutive terms. Okay. For you pick some I and you add the i's and the I plus first term. That's called a merge operation. This is for I from 1 up to the length of this root multiplicity minus 1. And what it means is that, okay, inside your cell corresponding to these root multiplicities, your roots that come with multiplicity omega I and omega I plus 1, they are distinct. Namely, the root of corresponding to with multiplicity omega I is smaller than the root corresponding to with multiplicity omega I plus 1. So here this one is like the, let's call this x1, xi. This is this root. This is the root xi plus 1, and they are inside a cell. They are in this relation. But now, if you approach the boundary, they can come closer and closer, and finally, in the boundary, these two roots coincide. And then, of course, both roots that have now come together, they bring with them their multiplicities. So the new root in the boundary has the sum of the multiplicities, and therefore we have exactly this root multiplicity in the boundary of our cell corresponding to the root multiplicity here. And the second situation is if you have a root multiplicity that does not yet exhaust the full degree. So there's room for complex roots. Then what can happen is, okay, I have two complex roots and say a conjugate pair of complex roots. And these two complex roots, they of course complex, actually complex, a non-zero imaginary part. When you approach the boundary of the cell corresponding to this root multiplicity, they can come closer and closer to the real line. So the imaginary part can shrink, get smaller and smaller, and finally the boundary gets 0. And you create a new root here. And this new root, of course, now immediately is of multiplicity 2. Because we came from two conjugate complex roots. So these are the two operations, merge and insert, that correspond to certain movements of roots inside the cell corresponding to a certain root multiplicity. And indeed, the lemma says that's it to describe the boundary. So if I have two root multiplicities, then the cell corresponding to the root multiplicity omega lies in the boundary of the closure of the cell corresponding to the root multiplicity omega prime, if and only if this omega can be obtained from omega prime by a sequence of these merge and insert operations, right? So, for example, in the case d equals 4, we get that we can look at the polynomials with no real roots, with 2 simple real roots, and with 4 simple real roots. Let's maybe look at the one with 2 simple real roots. Then what you can do is what can happen is these 2 simple real roots can come together and form a new real root of degree of multiplicity 2. So that's this path. Or, well, here there's space for one pair of complex conjugate roots, and they can come together. Well, I mean, we don't know where they come together. They could now come together and form a root which is smaller than the smallest root, or larger than the largest root, or just lies in the middle. And this corresponds to these three insertions. Okay, so we can insert the degenerate complex root in front of the two simple real roots, in the middle, and at the end. And then we can further degenerate. We can now go from that one here and start here. And then, okay, there we have a choice. We have no more choice. We have still choices, but we can only do merge operations. There's no more space for a complex root. So we can either merge the 2 with the 1, get 3, 1, the 1 with the 1, get 2, 2, and oh, there's an arrow. That's a okay. That's it. Sorry. All right. Okay, that's it. So we can merge the 2 and the 1, and the 1 and the 1, and this gives us the 2 resulting root multiplicities. The other arrow was incorrect. Okay, or if you start with polynomials with no real root, the only thing you can do is you have a complex pair of complex root come together and form a double real root, and then you can do more. Okay, so this is the combinatorial picture that will govern our studies. Okay. So then the claim is this PD omega for omega in the space of the set of root multiplicities, and the point at infinity, an additional point, they define a structure of a CW complex on the one-point compactification of the space of polynomials of degree D. Now, the space of polynomials of degree D is R to the D, our way we have topologized it. And if you take the one-point compactification of R to the D, you obtain the D sphere here. So all those PD omega give you a CW structure, not so trivial CW structure on the D sphere. Okay. So now we want to harness this structure and use it in order to understand the homological situation for spaces of polynomials with root multiplicity, with restricted root multiplicity. And for that, we need the following proposition. And for the sake of simple notation, here we identify a root multiplicity omega and the corresponding cell. Well, it's always easier to write omega instead of meaning the cell. And we have a CW structure, so we can consider cellular homology. So we have these cells, and we need to know what is the boundary of these cells in homological terms. And the cellular differential of this CW complex described here, this one, where you have a single zero cell, the point at infinity, and then all those PD omega for the various omega in capital omega D. This cellular differential is, after choosing suitable orientations of our cells, given in the following way. We look at the cell. As I said, we identify it with the root multiplicity. So the boundary of this cell is given by alternating sum of insertion operations and merge operations. Actually, the number of insertion operations. No, it's okay. No, insertion operations, right? Okay, sorry. So you insert wherever you can, if it's possible. I mean, if this omega already has norm D, then this one should be seen as empty, right? So you insert a 2 at every possible place, at the front, between the first two omegas, and so on, up to after the last omega, and then you subtract an alternating sum of merges. And again, these insertions and merges, they lead you to root multiplicities, but again, we identify them with cells. So you have a very nice combinatorial differential for your cellular chain complex. And this one, this is the key to what we prove later. So here, I mean, just to give the picture back. So this is this case d equals to 2, and if this is the space, and if you 1 point compactify it, then you of course you get a sphere, a 2 sphere. You have somewhere here you have the point at infinity, and then you have the parabola together with the point at infinity being an S1, and then they separate the sphere in 2 hemispheres corresponding to the 2 strata here and here. Okay. Of course, as soon as you start with d equals 3, 4, and so on, the pictures become very complicated and essentially impossible to draw. I mean, for degree D, you can still draw something. There's this famous swallowtail, but starting with degree 4, it's absolutely impossible to draw anything reasonable. Okay. So let us understand this differential I just described a little bit better. So first, I haven't only really explicitly said what is the differential of the composition of the root multiplicity d, which means I have one root of multiplicity d. So the whole polynomial is essentially x minus the root to the d. This is in the case when we have d equals 2. This was this parabola. And this parabola is together with the point infinity forms a one sphere, and the boundary of this parabola, of course, is 0. I mean, it's a one cell, and both boundary points are identified, so they cancel out. So this is 0, and this is the same what happens in general for general D. And also, if omega already has the only real root, is a root multiplicity for polynomials that have only real roots, then you essentially end up with some kind of simplicial differential. Here, this part is canceled, and this is very much looking like a simplicial differential, if you also take into account how these merge operations look like. Indeed, this is a simplicial differential on the simplicial cone of these polynomials with only real roots. So otherwise, you have to check a little bit what is the differential. So most of it's straightforward. One thing maybe interesting to say is that all the coefficients in the differentials will be plus minus 1, except sometimes it's 0, like for example here. Now, why is that? Because this composition 2, 2 here appears twice in the boundary of 2. Because this 2 means, by our semantics, you have a double real root. This is my double real root. And then the only thing you can do here, you cannot merge roots. You have only one root. So the only thing you can do is two complex conjugate roots, they can come together to a double real root. But now you have two choices. I mean, the complex roots can come together to the left or to the right of this double real root. In both cases, when they come together, they form the root multiplicity 2, 2. So 2, 2 appears in the boundary of 2 twice. And if you look at the coefficients of the differential, they cancel out. and suddenly you get a 0 here. So this is always something you have to be careful about. This essentially happens when you have a sequence of an odd number of 2's and you insert another 2, then the coefficient will be 0. Otherwise, all the coefficients are plus minus 1, except again for this last one, which is special, which takes this one sphere corresponding to the considers this one sphere corresponding to the root multiplicity D. Okay, so this is now we have complete combinatorial control over the situation. And now we need to understand actually what spaces do we want to consider. And we want to consider for some subset of our set of root multiplicities all polynomials that lie in root multiplicity from this subset. Okay, so this data is somehow described. You say all root multiplicities should be even or odd whatsoever. That's a subset, and then you collect here in this space. You collect the union of all those polynomials that satisfy this constraint on the root multiplicity. Now, in general, this will be an odd space, complicated, weird structure. It will be nice if it's closed, if you have a closed subset in the space of polynomials. And being closed as a subspace of the space of monic polynomials of degree D is equivalent that the set of root multiplicities I have chosen is closed under merge and insertion operations. Okay, so whenever I do a merge or insertion operation with an omega from my big theta, capital theta, then I again land in theta. And in this situation, I call theta closed itself. So in the case theta is closed, these cells for the omega in theta and my infinity again define a CW structure on my PD theta. And since I have closed theta under merge and insertion operations, the cellular differential is just the one I inherited from the cell decomposition of the sphere. So just to give you an example, if I choose here all theta, which have only odd parts, then this is not closed because it's not closed under merge operations. If you have two odd parts, then you merge them, and then you get a part which is the sum of two odd numbers. It's an even number, so you have left this one. But if you say it's, for example, it just has even multiplicities, that would be good. That would be a situation that is closed. Okay. Any more questions? No. So let's go back to the Arnold Vasiliev case. So what did they consider? Just to remind you from the very beginning of my talk, they considered the situation, the polynomials which have no root of multiplicity greater, no real root of multiplicity greater or equal to k. Okay. And now we want to model this in our situation. And we look at theta kd. That is the set of bad root multiplicities. Now, so Arnold Vasiliev, they have the situation where they consider no root of multiplicity k or larger. Now here we consider root multiplicities where actually one multiplicity is greater or equal to k. So these are the bad polynomials. The polynomials with those root multiplicities, they lie not in the space considered by Arnold and Vasiliev. But this one is good in the sense that it's closed. If you do a merge or insertion operation, this property certainly is preserved. So our corresponding space PD theta KD consists of all polynomials which have a real root of multiplicity greater or equal to k. Okay, so this is not really what Arnold and Vasiliev want to look at, but we want to look at the complement of the one-point compactification of this space inside the one-point compactification of all polynomials inside the sphere. Right? So this space, the complement of the space inside the space of all polynomials, one-point compactified, is all f where there is no real root of multiplicity greater or equal to k, because we have just removed all the ones that have a root multiplicity greater or equal to k, and we have also removed the point at infinity. So what remains is just a solid polynomial, and it must have a root of multiplicity greater or equal to k, because otherwise it would have been an element of PD omega kd. So this way we model in our situation the Arnold and Vasiliev case, and indeed we can also prove what they proved, except for the ring structure. And the other disadvantage is that, and for that reason we also don't have this proof in our papers, the proofs are more complicated than their original proofs. So we can obtain their results, we can reprove it, but their methods are very much tailored towards the situation, and they are more elegant than our general, but in some way brute force attack. What we are interested in and what we can prove is some type of stabilization result. Namely, whenever we have a root multiplicity, whenever we have a root multiplicity, say we have here a root multiplicity where there's a part greater or equal to k, and that sums up to something less or equal to d, and the sum is congruent to d modulo 2, then the same holds true if you replace d by d plus 2. So you can consider every element from this set of root multiplicities and element from this set of root multiplicities, and therefore you can also extend a polynomial with this corresponding root multiplicity to a polynomial here. For example, by doing the following: you take this polynomial, I multiply it by a polynomial that has no real root and is of degree 2. So we choose x squared plus b. Right? So this one starts with a polynomial of a certain root multiplicity omega that lies in this set. And here we get a new polynomial that has exactly the same root multiplicity, but now since we are in polynomials of degree d plus 2, this omega is considered as a subset of root multiplicities for polynomials of degree d plus 2. And this way we get a sequence of insertion operations, and we would like to understand stabilization results of when we now take the union of all these omega kd for d odd and even. All right. I mean, it's clear that it preserves the parity. So if d is odd here, d is odd here, d plus 2 is odd here, and if d is even here, d plus 2 is even here. So we have essentially now two cases, two stabilizations, one for d odd and one for d even. And this is what we want to study. And we want to study is not only for the situation from the Arnold-Vasiliev case, we want to study it for an arbitrary data in the odd root multiplicities, or from arbitrary theta in the even root multiplicities. Okay, and then we also get our theta d, if we intersect our root multiplicities with omega d. And in order to study that, we need a few technical functions, some set psi that assigns to a set of root multiplicities a certain number, depending on the maximum, go over a set MD. That is the maximal root, the maximal omega in this set, and then this expression here, where L of omega is essentially the number of parts of this root multiplicity. So it's kind of a technical function. And MD, as I said, is all omega in zeta d with the property that the corresponding cell is maximal in the corresponding space. Okay, so this is some technical functions that I wanted to write them down, but it's not super important to remember them. For example, I give a very simple example. If I start with an omega that is either an odd, so that the sum of entries is odd or even, then one can look at the zeta that is generated by this omega, namely the set of all omega prime that arise from this omega by a series of merge and insertion operations. And it's not bounded how many insertions you can take. You now don't have a d around. Oh, sorry, that's odd or even. You don't have a d around, so you can insert as many 2's as you like. Get an infinite set here. And for this set, the cell corresponding to omega is the maximal one, because insertion always will for every d you choose, you will decrease the dimension, and therefore you get here a very simple expression, because your MD will just consist out of this omega. So so your function psi is a maximum over a single element set, and you get exactly this number where omega is this L top. Okay, this is just a very simple example. As I said, the actual structure of these functions may be not so important. Okay, and then we have a theorem that says that in our situation, when we have given a set of root multiplicities of odd root multiplicities or of even root multiplicities that are closed, and if we have a j larger than this strange function, then the jth homology group and the j plus first homology group coincide for the space for the root multiplicity restrictions in polynomials of degree d and polynomials of degree d plus 2. So this means that, for example, in the Arnold Vasiliev case, you have a very well prescribed description of where your homology stabilizes. I've written this down here for a very simple case. Omega has 6 single real roots, and here you work this out, and the stabilization appears whenever j is larger or equal to 1/2 d plus 3. Okay, so this is one result we can obtain from our combinatorial description. And the same we get for the complement, which is just an application of Alexander duality. We get, of course, then everything turns around. J must be larger than something, and so on. Everything is a consequence of classical Alexander duality on the sphere. And then, without wanting to say too much, we have similar results for BD, for the space of binary forms. For example, we can describe completely the situation of double real roots or no double real roots, where here it becomes more complicated, because here going to the complement is not just simple Alexander duality, but you have to work with some local coefficients. So that's a bit more complicated. And then one also can wonder, now this is these are stabilization results here, but maybe with the help of our combinatorial differential for particular omega d, theta d, whatever your root multiplicity could be, say at least the root of multiplicity 15, what happens to the homology? And indeed, we have quite a few results on very explicit homology computations for this situation. But I think my time is over. I thought it's 50 minutes. So I thank you very much, and I'm happy to answer any questions.
Thank you very much, Professor Welker, for a wonderful talk. Professor Welker, can you give the reference of the paper from where
the
you're
papers,
talking?
I mean, we have 2 papers on arXiv. Just look at all the authors. I mean, I don't know. This is, let's go to the first page. Here it is, yeah. So Boris Shapiro, maybe it's also not completely visible. Here's a Shapiro. And Gabriel Katz and Volkmar Welker, there are 2 papers. So with Boris, I had more already a long time ago, but Gabriel, the 3 of us, there's only a single paper. Both are on arXiv, and you're
Thank you.
welcome to.
Thank you very much. Any question from the audience side? Okay, I think
I have one question. Okay. I'm just looking, is there any, I mean, your results give something like if we have some, that combinatorial data, and associated to that combinatorial data, we have some polynomial. So can we answer? Yeah. So can we answer using your result? I mean, I don't know. That about that polynomial has real roots, only real roots, or there are some complex roots, something like that. No. It's just like it's giving you
converse. It's a converse. I mean,
yeah.
If your omegas all fill up D, then your polynomials must all be real rooted.
Yes.
So you can if you want, you can restrict your considerations. If you look at omega, so I don't know. I mean, maybe where do I do that here? Maybe okay. Let me. How do we insert a word here? So for example, if D is 4 and your theta consists out of 1, 1, 1, 1, and then 2, 1, 1. And 1, 2, 1. I must now close, so that's a bit tedious. And sorry, 1, 1, 1, 2.
Yeah.
1, 1, 2. Then you have 3, 1, 1, 3, 2, 2, and 4. That would be, so the corresponding P d theta would be only polynomials with only real roots, but not all of them, some of them. So that would be, those were, well, just take those 4 single real roots, a double real root and 2 single ones, a triple real root, a single one, 2 double, and a 4, 4. And then you can understand this space. It's not that I mean that if I give you a polynomial, then I don't have a mechanism to figure out for which omega it is.
Okay.
So this is not the type of direction it works.
Okay.
There was a is that
question
okay?
in the chat. Yeah,
there was a question in the chat about insertion. So Shane, is that okay at the moment?
Yes,
or?
that's okay. Thank you. Thank you.
So there was a question about the insertion operation. So as I said, I mean, assume you have a polynomial. Say D is say 6, and you have a polynomial where here you have a single real root, and here you have a triple real root, and no other real root. So this corresponds to the root multiplicity structure 1, 3. And then you have one pair of conjugate complex roots, wherever they are. They could be here, they could be here, or they could be here. Now, if for them you let the imaginary part go to 0, they will come together to a real root. But since they are coming two conjugate complex roots coming together, it will automatically be a real root of multiplicity 2, because it comes from two complex roots. So if you insert it here, the root multiplicity pattern will be 2, 1, 3 afterwards. This is the dot. If it's here, it will be 1, 2, 3. And if it's here, it will be 1, 3, 2. Does this explain the question? I don't know who asked the question in the chat.
Junaid asked this question, and I think the insertion. Junaid, did you get it? Junaid, are you there?
No, maybe. Okay.
Probably he.
Okay, yes,
Yeah, he left.
No,
Okay.
he answered.
No, he is there. He has.
He
Okay.
answered.
Okay. Fine. Thanks.
Okay.
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 One more question from this this insertion. Maybe I'm wrong. Okay. For example, if we have these two complex roots are just lying have the same real part as a given real root, it
This
might be
one.
possible.
Yeah, that's okay.
Okay.
So if they come together, if they come together at this one, it will result in 3, 3.
Yes,
right?
3, 3. Yes.
But this is so this is some kind of this is a higher to speak so to say higher coincidence. It's essentially a degeneration of the situation that the root comes together here here to the left, leading to this, and then these real roots move to those. So
okay.
So
So this means that if we will merging them, then we can get this thing.
Yeah, I mean,
first insertion and then merging.
Yeah, so the statement says that if you have if you look at this, the open ball of all polynomials that have this root multiplicity 1, 3, then the polynomials in the boundary of this cell can have root multiplicities that can be obtained from 1, 3 by a sequence of merge and insertion operations.
Okay.
So what I described here is just the kind of the first, so the most non-degenerate step. I mean, your situation is kind of degenerate because or singular because it requires this complex root to have a specific real part.
Yeah.
But this is captured by additional merging and insertion operation.
Thank you. Is
that clear?
Great. Yeah, that's clear.
Thank you. Is there any other question or comments by the audience? Thank you, Russ, for sharing those papers in the chat. And thank you, Professor Welker, for a very, very nice introduction. And I think for those who are viewing this particular topic for the very first time, there is enough material, enough background you have explained for studying these papers. And it is really very interesting. Thank you. I hope to have more talks from you in upcoming year in the John Conway series. Thank you, everyone, for coming.
Thank you for the invitation. Okay, bye-bye.
Bye-bye. Take care.
Bye.